So to clarify the main difference between these two sets of notations with an example here, we'll take a function, say f of x equals, I don't know, 5 on x squared plus 1 to the fourth, something like that. Okay. So using the Leibniz notation, if we want to find f prime of x, well, I could view this as being y equals 5 on u to the fourth, and u would then be x squared plus 1. Okay. I have two separate functions. One is really a reciprocal function, 5 on u to the fourth, and I have another one that's a little polynomial, a little quadratic, separated out from this composition, right? So according to the rule then, dy dx, again using the Leibniz notation, should be the derivative of this one with respect to u times the derivative of u, right, the second one here, with respect to x. So calculating each of those, right, we would have du, again to write this out as explicitly as possible, of 5u to the fourth, right, times the derivative with respect to x of x squared plus 1. Okay. And of course for this one here, I would view it as 5u to the negative fourth when taking the derivative, and we would get the negative 4 coming down, negative 20, join with the 5, negative 20, u to the negative fifth, it's got to go down a power, it's a power rule, and times the derivative of x squared plus 1 should just be 2x. We have this expression. One of the main problems with using this type of notation is you have a mix of variables here, which you really wouldn't want at the end of the problem. So inevitably, you'll be forced to resubstitute the function you separated off from the composition back in at the end. So that's why I find this a little cumbersome and not that valuable for the context of these types of problems. Nevertheless, just to exhibit this because the book has many problems like this. So to finish this off, I would really like the derivative of y with respect to x, so therefore the variable here at the end should only be x. So I can replace the u here with x squared plus 1, and I can combine the 20 and the 2, of course, so I'll get negative 40 x squared plus 1 to the negative fifth, and then times x. Okay. But we don't want negative exponents in our results, so therefore I'll just switch this very quickly. We'll have negative 40x over x squared plus 1 to the positive fifth power, and there's our derivative, okay, using Leibniz notation. Now we could have done the same thing using the prime notation, and in my opinion it goes much faster, more efficient. So let's see, if we view f of x down here again, we see the composition, we see that x squared plus 1 has been put inside the fourth power function, but I would go ahead and write this as 5 x squared plus 1 to the negative fourth anyway, right? Just like I did whenever I was going to compute the derivative when I had u in here, right? Same thing, I still viewed it as a negative power. So now we just take the derivative, okay, f prime, without recourse to separating the two. There's no reason to separate the two. But we do see an inner function here, right? There's an inner function. and there's an outer function. The outer function is really the negative fourth power. Two functions, inner and outer. So the rule we had above said you take the derivative of the outer and leave the inner unchanged. That's the first part. Okay? So the derivative of the outer, the power rule here, the negative 4 will come down. So we'll have 5 times the negative 4. The inner function, x squared plus 1, does not change. But I'm differentiating a power function, so this has to go down to negative 5. Okay? So that's complete, right? For the first part up here. I have outer function derivative with the inner function staying the same. I simply need to complete this by multiplying by the derivative of the inner function. The inner function we said was x squared plus 1, which is easy to tell because it's inside the parentheses here. So the derivative of x squared plus 1 is just 2x. So now we just multiply by that derivative, 2x. And then we just simplify to finish off the derivative. So 5 times negative 4 times 2 is, of course, negative 40. So we have negative 40x divided by, we want this down the bottom where it has a positive exponent, x squared plus 1 to the 5th. Of course, yielding the exact same thing we had back here, but in probably a little more efficient manner, a little bit cleaner. Okay? Well, this is probably the preferred way to perform most of these problems.